Okay, well, we're well aware, because everybody here is in physics, and I've been browbeating you on this for a long time, of not only that the moment of inertia of a point mass, a particle, is mr squared, where r is the distance from the axis. But from physics, you should know why, in terms of energy conservation, all kinds of other things, hopefully. Okay, but you don't need all that physics to do this. You just need to know that the mass of a particle is mr squared, and we're treating this increment, the mass in this increment, as a massive particle, right? Okay? So, we've got mr squared, and we can draw a little picture here. We've got x, y, and z, and we got some point out here. Okay? What's this point? This point would be our xi star, xk ji star, yji star, zk star. I wrote that small because we should know perfectly well what that is. Okay? And you should draw that picture. And then you draw a little rectangular box around this thing. So you have some mass in it. And that is this increment, right? And its mass is this. And the only thing we have to know is how far it is from the axis. Okay, how far is it? Well, you told me. The distance from here to here is the same as the distance from here to here, right? Because this is vertical, so this all makes a square, a rectangle, right? Geometric argument. And we know that this distance is, you're going to want to say square root of x squared plus y squared, right? We've got to be specific to the integral. So it's xkji squared and yji squared. I'm getting used to the order here. I'm going to start screwing up the other one. Okay? And of course, that's r. That's your distance from the axis, right? And of course, you're doing r squared, so you can get rid of that square root. And you did when you told me. I don't remember whether you mentioned the subscripts or not, but I assume you did. So now it becomes very easy to write down the mass, or the moment of inertia, due to that increment. So, also, I could call this mass here, delta M, kji, right? Because again, everything is a kji increment. It's this. So we get delta I equals R, we'll call this RKJM, KJI. Now things are getting a little indistinct. I'm writing it. There it is. RKJI equals this. So it's RKJI squared delta M KJI, and that is just then X KJI squared plus YJI squared rho of X KJI YJI ZK ZI times delta X KJI delta y, ji, delta zi. Okay? Being careful with subscripts. But all we're doing is we're writing out mr squared for this increment. M being the delta m of kji we got here, and the r being the rkji we have here. Okay? Now that approaches an integral. And I'm just going to write this as triple sum of and I didn't put my stars on the x's and the y's here. Emphasizing these are the sample points, right? Now, I don't have stars on these, but so it's that sum, right? Where the z's are subscripted by I goes from 1 to n, j goes from 1 to m sub I, and k goes from 1 to p sub ji. Okay? So those are the limits as we notated them here when we finally got the notation straight. Well, this approaches as your delta x, delta y, and delta z all approach 0. Being a little vague about that because the notation gets a little cumbersome. Okay, but you understand that all the delta x and delta y's and delta z's go to 0. And there are many ways that could be notated. This then approaches the integral. Didn't leave myself enough room. Yeah, I got to start a new line. Still not sure I'll have enough room. Okay? So what? Your z goes from -3 to 3. And I don't have that on screen anymore, but we should remember that. If not, we can look back. Okay? And our y goes from the square root of 1 minus z squared over 9 negative to the square root of 1 minus z squared over 9. Right?
2 times that quantity.
Yeah, right. 2. Now, I didn't leave myself room for the 2 down here. It's going to look like a square root, so I'm going to have to fix that. I mean, it is a square root, but putting the 2 in there is still going to look like a square root. Make the notation as unclear as possible. -2 times the square root of 1 minus z squared over 9. And then from negative square root of 1 minus z squared over 9 minus y squared over 4 to the square root of 1 minus z squared over 9 minus y squared over 4. Of what? Rho of x, y, z. Well, x squared plus y squared, rho of x, y, z, dx, dy, dz. Right? And of course, rho of x, y, z is just x squared plus y squared plus z squared plus 1. Okay? So when this is all multiplied out, you'll have a fourth degree polynomial, okay, in both x and y. But that doesn't hurt anything. It's easy to integrate polynomials. Now, when you substitute this in, you will be substituting it into some odd powers. So you're still going to have to do some trig substitutions. Okay? Now let's set this up in cylindrical coordinates. Now, what's going to be easier if we set this up in cylindrical coordinates?
The r.
Yeah, r is just r, because that is the distance from the z-axis, which is why I chose to rotate about the z-axis. But the limits might or might not be simple, okay? Turns out they are. So go ahead and see if you can set up your inequalities. And one thing I forgot to do up here, or just neglected to do, I guess I forgot that I was going to do it. I put the limits down here in the partition. I never did write the inequalities up here, but the inequalities are obvious. Now this is going to be square root of 1 minus z squared over 9, 2. And this is going to be negative square root of 1 minus z squared over 9 minus x squared over 4. And this will be plus 1 minus z squared over 9 minus x squared over 4. Okay, well, okay, so all this leads to the integral. Now what do you get in cylindrical coordinates?